Hi, my name is Dylan, and the question I'm going to answer today for this video is how can we optimize gradient descent? So let's begin with some motivation. In machine learning, we are often concerned with minimizing some loss function of the form as follows. We have Fw equals the sum or average of several smaller Fiw's. Some common examples we've encountered is the square loss error in linear regression and the cross entropy error function here. And the Fi's are given as shown in the slides. So how do we usually find a good way to minimize the loss? This is usually hard to do analytically with computers, so we employ the idea of gradient descent. Gradient descent can be summarized by this one update rule, where for each iteration, we decrement our current W in the direction of the gradient, scaled by some step size ak. For good choices of ak, we can converge to a local minimum, which is a good enough way to minimize loss. Now let us look at the complexity of gradient descent. Each step of gradient descent is O of n time, which is clear when we just look at the equation here. This is not good for large n, which is usually associated with the number of data points in a machine learning model. Even evaluating each Fi might be non-trivial. For example, if we have high-dimensional data and Fi's. This is done several times, which can become very slow. So now on to the topic of the video. How can we optimize gradient descent? One method discussed in lectures and used in assignment 2 is mini-batching. Instead of calculating the exact gradients, we estimate it by choosing a small subset of data points and calculate the respective Fi's and then take the average. This equation here summarizes what I just said, where m is the size of the subset we take, which is usually much smaller than n. For example, we used 100 in assignment 2. The computational complexity now is O of m for each step, which is much smaller. Usually, this method still lets us find a good enough approximation to a local minimum, but it does have some cons, which is expected as we throw away some information when we take approximations. The rate of convergence is lower, and we may not even converge accurately. We know that the method of mini-batching actually lies in a whole class of stochastic gradient descent, or SGD methods. Any SGD method can be formally defined as follows. We have an update step here, where instead of moving in the direction of the true gradient, we now move in the direction of some stochastic gradient G. The stochastic gradient is assumed to have expectation equal to the true gradient, as shown here, and has a variance identity given below here. Next, we will provide a theorem about SGD. Although the statement may appear very complicated with lots of assumptions and variables, we will extract the two main messages at the end. So we begin with our assumption. Suppose f is continuously differentiable and Lipschitz continuous and gamma strongly convex. So f satisfies these equations here. Note there exist other equivalent definitions, but these are one of the ones we picked. The diagrams on the screen give some examples or non-examples of such functions. Then if we run SGD with a fixed set size alpha, satisfying these bounds, we get this identity on the expectation of the difference between f of wk and the global minimum f of w star, and hence this limit identity below. We won't go through the proof for the sake of brevity of the video, but the techniques used are actually fairly elementary. So what exactly is this saying? There are lots of variables involved, but we can pull out two main messages. I've put at the top of the screen our assumptions, the assumption on variance and some constant terms that talk about our variance, and about on our step size. Then we have our statements down here, the expectation that is bounded by some value here, and also the limit of the expectation. First, let's look at this identity on the left here. We have two constant terms here, and then a term depending on k, which is how many iterates we have on our algorithm. This constant here is basically our rate of convergence, and it's lower bounded by this value here from our choice of step sizes here. Gamma and L are fixed because they are determined by our function, but MV is what depends on our variance. Another thing we keep in mind is that this whole value here decays faster when it's smaller because we're taking its exponential. And if you do some identities, inequalities, you notice that the smaller v is, the faster this identity on the left decays. The second message is that we can also look at the accuracy of convergence. Now we consider this limit equation on the right here. We see that as the limit of k goes to infinity, the difference of f of wk minus the global minimum value is alpha lm over 2 gamma. Notice that this is non-zero. Again, here we have some constants that we can't really change. And then we have m, which depends on, again, our variance. So the smaller m is, the smaller the neighborhood of convergence we get. So what is the upshot of this theorem? Well, it's basically saying that variance is bad because it slows down our rate of convergence, and it gives us a worse accuracy of convergence as well. Note that we assumed in the theorem that our loss functions are convex, but this is not true for the general case. We can take neural networks with at least one hidden layer, for example. However, there are other theorems for non-convex functions. So to recap, SGD is usually faster to compute, but converges lower and may not converge to an exact minimum. However, there are a bountiful amount of SGD extensions. For one, we can choose variable step sizes, which allow more accurate convergence, but at a slower rate. There are also several recent papers which looks into ways of reducing variance by using information of old gradient estimates to reduce variance. On average, we spend more time on computing and using this information per step, but this leads to higher quality and faster convergence. We can also delve into other state-of-the-art methods, some of which are not necessarily SGD methods, but can be combined with SGD. For example, we can incorporate momentum methods, or even try descent on coordinates. We could also calculate or estimate curvature information to get higher quality convergence. There's a lot to be said about these methods, but unfortunately, we definitely cannot fit this discussion into the length of this video. So to answer the question we have proposed, we can usually conclude that vanilla SGD, such as min-imagine, is a good baseline improvement to normal gradient descent in terms of optimization. However, there are many more state-of-the-art methods which perform much better by balancing the trade-off of computational time and convergence quality. Most of these methods are even implemented in TensorFlow, and you can check them out here in this link below. Thanks so much for listening to this video, and I hope you found this intro to SGD quite interesting.